Okay, good morning, class. So we will start the lecture 5.2, yeah? So please have a look at 5.2. This last chapter, 54 slide, yeah? 54 slides altogether. Please check, yeah? So shall we start, class?
Yes, sir.
Thank you very much. Who is that?
Muhammad Ali.
Muhammad Dennis.
Ali.
Oh, Muhammad Ali. Yeah, thank you, Muhammad Ali. Very clear.
You're welcome.
Okay, so yeah, the notes are not available. So you can copy or you can take a snapshot. You take a snapshot, and then if you want to take down, and you can ask me to pause. So I will wait for you. So today's topic is still 5.2, yeah? 5.2. Let me know if you are copying anything. I can wait for you. You can write down the equation first, because the lecture notes is not uploaded yet. You got to wait. So I will go very slowly today, because this is the last chapter, 54 slides. We already finished about 15 slides last week. But previous lecture, we got some problem, some glitches, internet problem. So I will repeat again quickly. Then we move on to today's session. So I will start recording, yeah? I will start recording, yeah? So if you have any question, please type in the meeting chat. I will reply to you and I will attend to your question. Okay. So good morning, class. Please see the slide. So all the slides are there already. But the thing is, you may not have the notes yet. So I will go very slowly. Now, the lecture today is still we are in 5.2, finite difference methods for heat conduction equation. So I'm going to use this snapshot, yeah, to show you so that you can see what is happening on the screen. So finite difference methods, there are three methods. This one we already saw in the previous lecture. So I go through. If you if any things are not clear, very blur, and then you need more explanation, you can stop me at any time. So I'm very glad to explain to you. So there are three methods. These are the very famous methods. Explicit method, which we already seen last lecture, but we will do it again. And the second one is simple implicit method. That is our topic for today. We will focus on this only. And next lecture, the last one will be Crank-Nicholson method. So after that, week 11, week 12 is the last week. We will do the revision, chapter 1, 2, 3, 4. And if you have time, we can do it again, chapter 5. So as you know, these are the numerical method. For this 5.2, the finite difference method, to solve PDE, we only focus on heat conduction equation. Just focus on only. Because there are three types we saw: elliptic, parabolic, hyperbolic, wave, and then heat and Laplace. But we just focus on heat conduction equation. So for explicit method, write down, yeah. For explicit method, this is the equation you need. Explicit method. The two equation very famous. But you may wonder whether this equation you must memorize or it will be given. Most of the time, these two equations are given. The centered finite difference for del square t del x square. This is partial derivatives. This partial derivative can be written in the numerical form. Capital T is temperature, x is the distance. This is what we call centered finite difference. And then forward finite difference is temperature respect to time. So left hand side partial derivative, right hand side is the numerical calculation. So what is capital T? Capital T is the temperature. What is del X? Del X is the change in the distance. We call it step size in numerical method. And then del T is the change in the temperature. So all these values will be given in the problem for del X, del T, and so on. So the partial differential equation, PDE, this one, we want to solve numerically. So we have to change the PDA into numerical form. And that is the whole idea. We want to solve this del T over del T equals to K. K is the constant. Del square T del X square in the form of numerical solution. So that's why they use the word substituting. So you substitute del T over del T with this one. This is given, refer to previous slide, and K multiplied by this term. So all the terms will be explained clearly, and it's already done. So that's why we go very quickly. So if you rearrange this equation, this is called rearranging. The T superscript L plus 1 should be on the left-hand side, this term. Because the L is the level. Later you see the figure. L is the level. The I is the for the X, X1, X2, X3, X4 like that. So the displacement, you have del X. So the X1, X2, X3, X4, X5, you want to calculate in between, for example, X0 to X5. So X1, X2, X3, X4 is the subscript I. So if you write this equation, rewrite T superscript L plus 1 subscript I equals to this one minus T superscript Li is here. And then K multiply del T over del X is called lambda. This is as per convenient. Yeah? So nothing much than that. Just as per convenient, we want to write in the nice form. This equation we must have. The rest, not necessary. The T superscript L plus 1 subscript I equals to T superscript L subscript I plus lambda in the bracket T superscript L subscript I plus 1 minus 2 superscript L subscript I plus T superscript Li minus 1. So the L always start from 0. You must remember L starts from 0, I starts from 1 because here got I minus 1. So this term, so I cannot be 0. So I must be 1. But the value for X distance starts from X naught because the next one is X1. We shall see that later. So this is the beginning for the what we call explicit method. Whenever you say explicit method, we need this equation. Of course, the lambda you can calculate K delta T over delta X squared. This one you cannot change. So you can copy this equation, you need this. So we will repeat this equation every time when you do the iteration. So what we saw in the previous lecture, this diagram, this computational molecule for the explicit form, for the explicit method, this is the grid point diagram. The cross is for time difference, T superscript L plus 1. This is the superscript L plus 1 is the level. This one is the x-axis, time. T superscript L, and x is the distance. This is the y-axis, xi minus 1, xi plus 1. So this is two the main problem, yeah, the inputs, the time and the distance. So you have to calculate the temperature. The temperature depend on time, x-axis, y-axis is the x, but the time depend on the level, L. So you take note, yeah, the level is called L. This L we have to fix it, and we will fix it, and the I we will fix it. This is xi minus 1, that means the previous x. This is the current x. This is next x, I plus 1. But the y-axis, the x-axis, T superscript L. L is the current one. The next time depend on the next level, L plus 1. So we can fix L0. When L0, this will be T power 0. This is T power 1. But you cannot see this in the equation. It's not available. Now, this is the problem we already solved last week, but I run through the slide quickly because we are solving the same problem by using the three methods. Explicit method, implicit method, and Crank-Nicholson method. So one problem, heat conduction equation, you can solve with the three methods. So if you ask to solve using any method, you can select. Why we give three methods? Because there is improvement, enhancement in the final output. These three methods will have a different solution. But which solution is the best solution depend on the convergent criteria and the error analysis and the stability. That is the end game of this topic. So the first method, you already, currently we are doing this, and we already done this last week as well, explicit method. But today we will do implicit method. So this rod is 10 cm. Del X is 2 cm. That means 0, 2, 4, 6, 8, and 10, like that. So when X0, that means your length is 0, then you move to X2, then 4, 6, 8, 10. So the step size is called del X for the length. The del T is the step size for the time. So the time, you are given del T 0.1 second. Now, at the T0, at the time 0, the temperature of the rod is 0. The capital T is 0. And this is called initial condition. Single variable. When the time 0, the temperature is 0. This is what we call initial condition. But the boundary condition is different. Boundary conditions are fixed for all time. So the temperature at any time, but at X0 is 100 degrees Celsius. X0 means that is the length 0. So the temperature, the capital T, is 100 degrees Celsius. At the length 10 cm, the temperature is 50 degrees Celsius. That means in the at the rod, yeah, the starting point at X0 is what we call hot, HOT. And at X equals to 10, that is what we call cool, COL. So the temperature is decreasing. So we want to know, of course, you want to find the temperature at T0.2. T0.2 means the next T. But the next T is 0.1, and the next one is the T actually 0, and then T at 0.1 we have to calculate, and then T at 0.2 we have to calculate. So the del T is the change in the interval. So in order to calculate T0.2, you have to do 2 times. At T0.1, that is at the level 0, and then at level 1, T 0.2. So you have to do 2 times. So the K value is 0.835. Now the question is find the temperature at T 0.2. So the temperature at 0.1, capital T at 0.1, not found yet. So we have to find that and then use that to find T02, which we already done in the previous lecture. But previous lecture, I think there was some problem. So we do it again. So now we call it the level, this level T 0.1. So at this T 0.1, you want to calculate the temperature, capital T. So in this case, your L is 0. So T superscript L plus 1 subscript I equals to T superscript L subscript I plus lambda T superscript L subscript I plus 1 minus 2 superscript L subscript I plus T superscript L subscript I minus 1 is the equation. This is the starting equation. This equation will be given, or you can refer. And the lambda is given like this. So first step, you find the lambda first. First step is to find lambda. So how do you find lambda? You need the K value. So K is 0.835 and del T is 0.1 and then del X is 2 power 2, 4. So you calculate 0.835 multiply 0.1 divided by 4, you get this answer, 0.020875. This is lambda. So take this lambda, substitute inside here. So when we say level T 0.1, the L is 0. Write down, yeah? The L is 0. So we can start now the first I. I equals to 1, X is 2 cm. This one is the initial condition plus with the boundary condition. The boundary condition is this one, this one. This T naught superscript naught is 100. The L on the top 0. This one subscript 0. That means the X is 0. This one at X is 5. This is the initial condition and boundary condition given in the problem. So you must know that T1, T2, T3, T4 all 0 degree. Because this is at time T0, time 0. So the temperature is 0, 0, 0, 0. Now at I1, X is 2 cm. Using the formula, using this formula, you set L0, L fix, L0, I1. So you are finding T11 equals to T naught 1 plus lambda 0.020875 in the bracket T superscript naught subscript 2, I plus 1, 2, I is 1. So at I1, X 2 cm. At I2, X 4 cm. At I3, X 4 cm. At I4, X 8 cm. I5 is this one, given already. So you no need to do at I5. You stop at I4 only. So this one minus 2 Ti L0 subscript 1 plus T superscript L0 and then subscript 0. So the I cannot be 0, must be 1. So that's why I1 X to cm. Use your calculator, calculate this value, make sure you get 2.0875. Make sure all of you can get this value. Can you use your calculator, calculate please? Can you get 2.0875? Hello? Can you get the value? Muhammad Ali? Okay, Natasha. Okay. What about others?
Yes, sir. Yes, sir.
Who is that?
Yes, sir, got the answer.
Muhammad Ali. Okay. We haven't done this, right? We haven't done this, right?
We did last
Not
class.
yet, right?
We did last class, I think.
Huh? Last lecture.
Yeah, I think so.
Have you done this? Yes or no, please? One Amir. Last
Yeah,
lecture.
I
Last
I
lecture. Huh?
I copied this last lecture. I think you explained this part already. I'm not sure. I
Or
think so.
what about others? Others? What about others? Shah? Just now one Amir, right?
Yes, sir. Yes, sir. Just now what
Okay, thank you. Okay, I will repeat again. So for I1 at x2 cm, t superscript subscript 1, 2.0875. Now, this is at t 0.1, yeah? At time 0.1. So at I2, x 4 cm, but the initial condition, boundary condition, they are the same. You cannot change the initial condition and boundary condition unless you are not given. Since this is given, so you make use of these values. So now at I2, x is 4 cm. So I2 means T subscript 2 superscript 1. So the L on the left hand side always will be T superscript 1. That is T superscript 1 when L0. So the right hand side you fill up T superscript 2 subscript 2. T superscript 0 subscript 2 is 0 plus lambda 0.020875. T superscript 3 superscript 0 subscript 3 is 0 here. Take this value, put it here, 0. And then minus 2 T superscript 0 subscript 2 0, and then you plug in here. And then T superscript 0 1 is 0. So you calculate all this, it will turn up to be T superscript 1 subscript 2 0. So for I2, the temperature T superscript 1 subscript 2 is 0. Now, you apply the same formula for I3. I3 X change, X is 6 cm now. So we are moving from 0 to 10 with the step size delta X2. So we already computed for 2, 4, now 6, next one is 8. That is the last one. So at I3, when T subscript 3, the subscript is very important because the L is fixed, L is 0. So L, no change. T0 subscript 3 is 0. Take this value, plug in here 0. And lambda is 0.020875 in the bracket T superscript 0, I is 3, 4. So T04 is 0 minus 2, T superscript 0, 3, 0 plus T superscript 0 subscript 2, 0. So you calculate, it will be equals to 0. So T subscript 3 temperature at x 6 cm is 0. And the last one is T I equals to 4. Previous one is I equals 3. Now I equals to 4. So you substitute I, T subscript 4. Superscript, no change. Subscript change equals to T superscript 04 is 0 here. Plus 0.020875 in the bracket. This one, T superscript 0 subscript 5 is 50. This one you have to be careful, 50 here. Minus 2 multiplied by 0. This is 2 superscript 0 subscript 4, 0. Plus T superscript 0 subscript 3, 0. So you calculate this, 50 multiply by 0.020875, you should get at least 4 decimal place, 1.0438. Of course, you can move on to 6 decimal or 5 decimal. Minimum is 4 decimal. So now I4 you already found. So we collect I2, I1, I2. I'm going now at slide number 12. I1, I2, I3, I4. So we put the solution like this. Now you use this solution, you have to do one more at T0.2. At T0.2, this one is a homework, yeah? You do it yourself. At T0.2, your L must be 1. So you go back, you check this equation, this equation, and you must change this L will be L if you substitute L1, so this will be T2. I will be still, for example, you are starting here. TL is 1, so T superscript 2 subscript I1 equals to, write down here, TL1, your I is 1. So 2 superscript 1 subscript 1 plus lambda, write down here, T superscript 1, I is still 1. So I1 at x2 cm. So I1, 1 plus 1, 2. So this term will be 2 T superscript 1 subscript 2. I is 1 minus 2 T L is 1. So T superscript 1, I is 1 plus T superscript L 1, I is 1. 1 minus 1, 0. So class, your T left hand side is superscript 2. This one T superscript 1. And all these inside the bracket T superscript 1. So you want to substitute T11. T superscript 1 subscript 1. The first term, yeah? This one, when you substitute L1, this is 1. So for that, you go here. You have to select this one. So T superscript 1 subscript 1 is 2.0875 plus I'm doing now for T0.2 for the first one, I equals to 1. And then I equals to 2, I equals to 3, I equals to 4, you can do it yourself. So now you already have T11 is 2.0875 plus lambda. So you go back, we are doing plus lambda. So lambda is 0.020875 multiplied by T21, T superscript 2 subscript 1. T superscript 1 subscript 2. So for that, you go back here. This one, this value. T subscript 2 superscript 1 is 0. Minus 2 multiplied by T11 is 2.0875 plus T01. T superscript 1, 0. T superscript 1, 0. So T superscript T superscript 1, T superscript 1, level 1 at 0. So you have T1 so T superscript 1 subscript 0. That means temperature at x0. 0 will be 100 degrees Celsius. Okay, so you substitute T0 at level. This one actually, sorry, this one will be level 1 means actually T00. So this one is actually equals to this 100. This one. Yeah. This one actually is T00. This is the initial temperature. You see the X is 0. This is the subscript 0. So you look at the subscript first. So now you calculate. You calculate the value for T superscript subscript 1. Can you calculate now? 2.0875 plus lambda 0.020875 in the bracket 0 minus 2 multiplied by 2.0875 plus 100. This one plus this value is the T naught naught. So this will be same as T10. So what is the value, class? Can you give me the value now? This is at X 2 cm, I1. So T11, you have this value, 2.0875. Yeah. What is the value? Now we are calculating at T0.2, the T superscript 2 subscript 1. Anyone can answer? 2.0875 plus 0.020875 in the bracket 0 minus 2 multiplied by 2.0875 plus 100. Yeah, anyone can answer, class? Yeah, one Amir. But we are checking now. The answer is 4.08967. 4.08785. Which one is correct? But Trisha, we are doing again this. This one is a new exercise, right? Of course, you did at home. Yeah, which one is correct? Shah or Shakir? 4.08, 2.0875, 5 decimal places, yeah? 2.0875 plus 0.020875 in the bracket 0 minus 2 multiplied by 2.0875 plus 100. Yeah, anyone? Use your calculator, but the answer given by Shah is 4.08785. It's different from 4.08967. Same with Shah. One Amir, same with Shah. Anyone else? I got same with Shah. Shakir, Ayman, could you please check again? Shakir, could you please check again? Check again. Please check again. So what is the answer, Shakir? Mine is wrong. Oh. So the answer is Shah is 4.08785. So this one class is T1 superscript 2. So thanks, Shakir. Thank you very much. Shakir, 4.08785. 4.08785. Yeah. Okay. So class, this one we found T 1, 2. At I2, T subscript 2, superscript 2. So you have to calculate T2, 2, for example. Yeah. Now I2, yeah. T superscript 2, subscript 2. I is 2 now. I is 2 means at X 4 cm. Just now X at 2 cm. So the subscript is very important. T2 superscript 2 is equals to T1, I is 2. T superscript 1, I is 2. Plus lambda, must write down, yeah. T superscript L1, I is 2. 2 plus 1, 3. Minus 2 superscript L is 1. I is 2. So T subscript 2 plus T superscript L. L is 1. Subscript I is 2. T minus 1, 1. You must practice, yeah? Otherwise, you will have a big problem later on. So now we want to substitute T2, 1, right-hand side. So you go here, T2, T1, 2, superscript 1, subscript 2, 0, plus lambda 0.020875, T1, 3, 0, plus 2 multiplied by T1, 2, 0, plus T11. T11 is 2.0875. That's why just now is 100. Now T11 is 2.0875. Can you calculate now, class? 0 plus 0.020875 in the bracket, 0 minus 2 multiplied by 0 plus 2 multiplied by 0.875. T2, 2. Temperature at superscript 2, subscript 2. So this is at I2, yeah? Please give me the value. Yes, please. Yeah, you can write down the value. I repeat, yeah? T superscript 2, subscript 2 equals to 0 plus 0.020875 multiplied by 0 minus 2 multiply 0 plus 2.0875. Yes, one Amir. Shakir. Yen Cheong, are you there? Chia, what is the answer, Chia? Please give your answer, Chia. Chow, are you there, Chow? Roger? Yeah, anyone? Can you give the answer, please? Chow, yeah. Are you sure? 0.04358. Anybody? Anyone can verify the answer? 0.04358. 0.04358. Patricia. Shah, correct, sir. 0.101. When can? You are there. When can? 0.0443577. We can make it 1, 2, 3, 1, 2, 5 decimal places enough. Okay, 6 decimal. When can Patricia Chow or okay. 0.04 0.04358. This is 5 decimal places. So for now, what we do is finding the temperature at 0.2. Yes, sir. Yeah, but we have to find at 4 different x. Yeah, at T 0.2, you have to find the temperature T1, T2, T3, T4. T1, T2, T3, T4. Now T2 ready at I2. Sir, Roger, now we are finding the temperature at 0.2 second. But there are 4 different temperature. The 4 different temperature at X2 cm, you got 4.08785. And at X4 cm, that is at I2, you got 0.04358. Now you can calculate at I3. You calculate just now, I1 already done. I1 is the T subscript 1. I1 T subscript 1. This is T subscript, yeah? So why the lambda we use for the equation is still using the lambda for, yeah, lambda same, you cannot change. Same lambda. Lambda is constant, yeah. Because the del T is 0.1. You see, the lambda, you cannot change. Lambda is constant. Lambda depend on del T class. See this one. It's not T, del T. So del T is 0.1. Lambda depend on del T. Good question, Roger. Lambda depend on del T. So your del T is fixed, 0.1. Okay. So now your I is I2 finish already, I1, I2, I3. So you substitute here I3. So you will have T3, L is 1, 1 plus 1, 2. Superscript same. So T3 to T superscript L1, subscript I is 3 plus lambda 0.020875 in the bracket T superscript L. L is 1, subscript I plus 1, 4, minus 2 T superscript L1, I is 3, plus T superscript L is 1, subscript I minus 1, 3 minus 1, 2. So you must practice class. If you don't practice, it's very hard for you. So you go back to this matrix, you substitute T31, T130 plus 0.020875. Practice, yeah? T14, T14 is 1.0438 minus 2 multiplied by T130 plus T210. So you calculate now. 0 plus 0.020875 multiplied by 1.0438. The rest are 0. So what is the answer? T3 now. Yeah. So anyone? T32. Easy to calculate. Yeah, very fast. Yes, Shah already answered. Anyone can verify, validate, test the answer, please? 0.03001. Yeah. Yeah. Can you check, please? Roger? Yeah, Roger, waiting for you. Yeah, 0.020875 multiplied by 1.0438. Yes, please. Roger? Yeah, this is very important iteration. Now we are doing the second iteration. Yeah. Anyone else? One Amir? Can you verify one Amir? One Amir. Yeah. Batrisha. Farasha. Why so different? 0.02179. So wrong, sir. Roger. Roger said mine wrong. Shah. Wrong, sir. Shah is wrong. So mine is wrong. Natasha, 0.02179. 0.02179. Farasha, okay. And then Roger, okay. Natasha, okay. So can we confirm 0.002.179? Yeah, good. Others? Anyone disagree? Anyone disagree? This is what we call computational experiment. Yeah, you do it yourself so that you have good experience on this. Next time will be very easy for you. Anyone? This is the right time, right place to check, validate. One more. Could you verify? Anyone else? One Amir? Are you there? One Amir? Yeah. Roger, are you okay, Roger? Roger, all right. Yes, sir. I'm here. Still loading, yeah. What is answer? Roger Wong, what is answer? Roger already replied. Okay. What about others? When? Wenkan, are you there? So can we confirm the answer, please? 0.02179 at I 3. Okay, so now we do the last one at I4. So I4, so you go back to this equation, the same equation, L1, so L is 1, so T 1 plus 1, 2, I is 4. So T4, subscript 4, T superscript L1, I is 4, plus lambda 0.020875 in the bracket T superscript L1, I is 4. 4 plus 1, 5. Minus T superscript L1, I is 4. Plus T superscript 1, I is 4. So 4 minus 1, 3. So I repeat, yeah. T superscript 4, 2, left hand side. This is at I4 at x equals to 8 cm. T superscript 2 subscript 4 equals to T superscript 1 subscript 4 plus 0.020875 in the bracket T superscript 1 subscript 5 minus 2 superscript 1 subscript 4 plus T superscript 1 subscript 3. I minus 1, I is 4. Now T14, so you go back to the last slide here, slide number 16. T superscript 14, answer is 1.0438 plus, write down, yeah, 0.020875 in the bracket T superscript 15. T superscript 15 is this one. This one is 50. So this is 50. T superscript 15 exactly is same as this. The subscript is important class. The subscript is important. So this is the value, this same value, 50. Minus 2 T14. T14 is 2 multiplied by T14, 1.0438 plus T130. Now you calculate. Same like this, yeah. You see T05 and T15 also is 50 because this is at x5. This one at x5 cm, sorry, at x10 cm, the temperature is 50, like this. So now you calculate, yeah, 1.0438 plus 0.020875 in the bracket 50 minus 2 multiplied by 1.0438, the plus 0. So what is the answer? This is the temperature at T4. Yeah. Still loading. Okay, one Amir, we are waiting for you. So this is the last one, yeah? At T0.2, temperature at T4. 1.0438 plus 0.020875 multiply in the bracket 50 minus 2 multiplied by 1.0438 plus 0. Yeah, please calculate. Yeah, this is a good exercise. You must do, otherwise you will have problem later on. If you don't practice, it's very hard for you. So you have to write down everything numerically. This is how it works, class. So this numerical calculation is like that. Okay, Roger, your answer, please. Yeah, Natasha. Waiting for your answer. Wenkan, are you there, Wenkan? Farasha 2.04392. Natasha. Azim 2.04397. Shakir 2.04. Wenken 397. What answer? Wenken. Same means what? 0. 2.04397. 2.04397. Purushothaman. Shakir 2.04397. 2.04397. Azim. Natasha. Okay, excellent. 2.04397. Excellent. Yeah, good. Very good. Okay, so confirm P4 2.04397. So you can build the matrix now, class. Well done, yeah. So you can build the matrix now at T 0.2. Build the matrix. Left hand side, right hand side. T superscript 2 subscript 1. Answer is 4.08785. Write down, yeah. This is what you are going to do. This is how you have to answer the question. 2 superscript 2 subscript 1. The left hand side, you fill up. You do this matrix. You write now. T superscript 2 subscript 1. 4.08785. T superscript 2 subscript 2. Answer is 0.04358. So now change. You see, change already. T subscript 2 superscript 2 0.04358. And then the third row, T subscript 3 superscript 2 is 0.02179. And then 2 subscript 4 superscript 2 superscript 2 subscript 4 2.04397. Write down, yeah. This is complete. Now you already solved the problem at T 0.2. So you get 10 over 10 marks. T superscript all same. You see the superscript all same. So that means you are really echoing this T 0.1. This one is at T 0.1. This is called first iteration. At T 0.2, you have, now we are doing second iteration. If they ask at T 0.3, you will make use of this. So that's why you must be very familiar with this equation. This equation is very important. So you can try at T 0.3, but it is not necessary because in the problem, you ask to find at T 0.2. If they ask you to find T 0.3, then you have to do one more iteration. So that is a good exercise and you have done. Any question, class, so far? Any questions? Any question, class, so far? So why we are not include the x0, x5 in the answer? Already given. Already given. This one is already given. Already given. X0, the temperature is 100. X0, X0, your T is 100. Yes, no need. X5. Yeah, good question. Yes. So you have to do a lot of investigation. So now the question is, if you still not satisfied, you can try at X at T 0.3 second. Homework, you can go and calculate if you want. So you go like that. This is what we call numerical method. This is what called iteration. You continue at T 0.3. You have to calculate I1, I2, I3, I4 again. So the temperature, the x-axis, you see this diagram. So you go back to this. So the x-axis is the vertical axis. So you can plot the graph. You can plot the graph. X-axis is the distance and the t-axis is the time. So it started with 0, 0.1, 0.2, and then 0.3. So the x-axis 0, 2, 4, 6, 8, 10. So 0 and 10 is given, this one. So you got to see the problem. This you study this carefully, class. So this is the thing. So at x0 is 100 degrees Celsius. At x10, 50 degrees Celsius. So now this method is yeah, just average, not that very good, because we are going to study another method. So today, just for the last part, I want to introduce this method, and we will do this in the next lecture, the exercise. So we will continue with this. So we already finished explicit method. You must know explicit method. It's already done. Now implicit method. Implicit method. So what is this implicit method? So in this lecture, we are going to do implicit method. So implicit method, the spatial derivative is approximated at an advanced time level. The time superscript L. So here, the advanced time level is the next one, L plus 1. So this implicit method is very important. This is second method, class. We can solve the same problem, which you already done just now, explicit method. But the formula is different. So for this, your del squared T del x squared is written this way. So this is slightly a different form. So you must have this equation. You no need to memorize. This is just to give you an idea. T superscript L plus 1 subscript I minus 1 minus T2 T superscript L plus 1 I plus 2 superscript L plus 1 subscript I minus 1 is called centered finite difference to represent del squared T del x squared. For the forward finite difference, del T temperature respect to time equals to T superscript L plus 1 subscript I minus T superscript L subscript I divided by del T. So Now we want to use this equation and we want to form the matrix. So here, the del T over del T is T superscript L subscript I minus T superscript L subscript I equals to K multiplied by T superscript L plus 1 subscript I plus 1 minus 2 T superscript L plus 1 subscript I plus T superscript L plus 1 subscript I minus 1 delta X squared. So the formula looks similar, but the way we want to write is different. We want to solve in a different way. This formula, the del T you can bring right hand side. Now you can what we call simplify this. You can simplify this. What you do, you rewrite again. So can you simplify this equation now? So you simplify T superscript L plus 1 minus T superscript Li. This term, this del T K over del X squared is lambda. So this lambda goes here. And TL plus 1 all left hand side. Write down, yeah. This one L plus 1. The right hand side only TL. So this term all combine with this. Okay. We put it here. So this is how you have to simplify this. Minus lambda. So you bring K del T over del X lambda. So you are minus lambda T L plus 1 I plus 1. This one become minus here plus 1. This one plus 2 lambda TL plus 1. This one minus TL plus 1. This one, yeah, sorry. TL plus 1, I plus 1 is this term. This one is here. And this T superscript Li is this one. So you may use the same equation as previous method, but the way you express is different. So this is the difference, class. So this one, we are going to create a matrix and we want to use Gauss-Seidel method. So the approach is different. So you may wonder if they give you this method, implicit method, which we are talking now, implicit method, you must have this equation with lambda K del T del X squared. Lambda is still the same form, but the way how you express is different. So you collect all the T superscript L plus 1, left hand side, T superscript L, right hand side. So this equation normally you will be given or you can refer. If they ask you to use this method, simple implicit method or implicit method, you change the form only. The form is very important. Because if you do it in what we call explicit way is like y equals to fx. Implicit is fxy together. So this is implicit equation. So explicit equation is different form, but the original partial differential equation still the same. But the way how you represent is different. Because here, T superscript L plus 1, T superscript L plus 1, T superscript L plus 1, all left hand side. You may say, can I write all these right hand side and T superscript Li left hand side? No need, because this is how you want to create the what we call trigonal matrix, and then we want to use Gauss-Seidel method. That is the purpose class. So you must familiarize and you must use this equation very frequently, because end of the day, if you ask to use this method, where to start? So you cannot modify this equation as you like. You must write like this. So the easiest way to memorize this is the superscript L plus 1 all one side. That's how we memorize this. And T superscript L is right hand side. And lambda K del T over del X squared. So using this, we want to solve the same heat conduction problem. But there is some information here. So we have to do some modification in this equation. Let us see the next slide, slide number 19. This equation applied to all, but the first and the last interior nodes which must modify to reflect the boundary condition. So this is what we have to modify to reflect the boundary condition. So the boundary condition at the left end of the rod at I0 can be expressed by T subscript 0 L plus 1. That's why this is what they said here, L plus 1, advanced time level. Advanced time level. So this L plus 1 subscript 0 equals to F0 T superscript L plus 1. So, but by substituting this condition, the difference equation for the first interior node, I equals 1. Just now at X is 2 cm. So 1 plus 2 lambda, 1 plus 2 lambda, this term goes to left hand side. 1 plus 2 lambda, T subscript 1, I. This one, I is 1. L plus 1 minus lambda T subscript 2 L plus 1 equals to T11. T11, sorry, this one. T11, I1, L1. T1, L1, L plus your lambda, this one, this term goes to right hand side, plus lambda. T0, L plus 1. I is 1. 1 minus 1, 0. So 0, L plus 1, this thing, substitute with this. This is the boundary condition. So at I1 is like this, but at I equals to M. So these are the interior node. I equals to M is like 2 cm, 4 cm, 6 cm, 8 cm. You have this equation now. Now this one becomes the general equation. So what is this class? Minus lambda T superscript L plus 1 subscript M minus 1. So I equals to M plus 1 plus 2 lambda T superscript L plus 1 subscript M equals to T superscript L subscript M plus lambda F subscript M minus 1 T superscript L plus 1. So for all the interior node, for example, X2, 4, 6, 8, the resulting set of M linear algebraic equation as M unknowns. What is the meaning class? This one, for all the interior nodes, you create a matrix. This matrix must be what we call square matrix. Square matrix means the number of equation same as number of unknown. Like just now you found T1, T2, T3, T4. So you will create a matrix 4 by 4. That means 4 linear equation with the 4 unknown. So the unknown are T subscript 1, T subscript 2, T subscript 3, T subscript 4. We fix the example. It's a good example. We learn all these methods using one example so that next time you can do the comparative studies. So using this equation, I equals to M, you create M linear equation. So we will use this equation later. Now you see the background of this study. So all this is about the space and time. Distance is the y-axis, xi minus 1, xi plus 1. But the x-axis now is t superscript L, and the next level is t superscript L plus 1. This is what we call grid point. So the intersection is here. This one is the one you're going to find the t at L plus 1 at the current xi. So in order to do that, we have to study Gauss-Seidel method. This Gauss-Seidel method, you have to design or construct using this idea. We will do this. And you may wonder whether you want to memorize this equation or it will be given. But most of the time, you no need to worry. It will be given. So you no need to memorize this. Okay? You no need to memorize this. It will be given. So this one, we have to do further investigation later. But the idea here is for the this method, what we call for the implicit method, we will use implicit method is to develop this equation. And then to solve the system of equation, we must use Gauss-Seidel method. This is different now. So Gauss-Seidel method is what we call a sub-method. So implicit, this one, this is the framework is like this class. This implicit, when they say implicit, write down, yeah, implicit method. The implicit method is to construct the system of linear equation. You construct the system of linear equation. That's all. That is the job of implicit method. But to solve the system of linear equation, we must use Gauss-Seidel method. So implicit method is not solving the heat conduction equation. No, we will use Gauss-Seidel method to solve the heat conduction equation. So here we have two methodologies. That's why this is more advanced and more stronger version. So what is Gauss-Seidel method? This is linear algebra. You studied in engineering mathematics 1, but in engineering mathematics 1, you study numerical method. Gauss-Seidel got two types. One is numerical, one is analytical. But we are not solving analytically. No, we must use numerically. The question is here, because this is the topic is about numerical method. So there is no question of using analytical method. Even if you want to compare, you compare among them numerical method only. So it is sufficient enough. We will study 3 different methods. We already finished explicit. Now we are currently doing implicit. And then the third one is Crank-Nicholson method. So Gauss-Seidel is the most commonly used iterative method. That is the keyword class. So when we say iterative method, you cannot use the analytical method. No, because iterative method means like what you have done at t 0.1, you already have the 4 values. At t.0.2, you repeat. This is called iterative method. You didn't use this word when you study chapter 4, Euler, Yoon's method, and Range-Kota. All these three methods in chapter 4 is iterative method, but we didn't use this word because we just use the repeated process. You repeat. We don't use. But now is very important because this is advanced level. So we use this keyword iterative method to solve what? Solve linear system. What is this linear system? AT equals to B. This is very important. A is the matrix. It's a general, what we call acronym or the notation for matrix. T is the temperature and the B is constant. That's why they want you to write this form. So you can create the matrix. So you can create the matrix using this or this equation. Yeah, either one. So this one modified and then they got it this equation. This one. So this equation is the system of linear equation. So you must familiarize. You must use this frequently. Try to practice. So this method is also known as method of simultaneous displacements, meaning solving simultaneous equations. You know, in algebra, it's very famous, solving simultaneous equation by using various methods analytically. But now is the time you want to do numerically. So we encourage you to solve this numerically. That's why you have to practice. Otherwise, you will not be able to do. So we can start the solution process by choosing the initial guess. When we say numerical method, how to start? So everyone use any values for initial guess. But here, this is the suggested idea. The simple way to obtain the initial guess is assume that they are all zero. What do you mean by this? So this is what we want to know, the initial guess. In the past, you may not come across this initial guess. We call it initial condition and then boundary condition. But what is initial guess? That means you assume something to start off the process. But this assumption based on knowledge or experience, practical or theoretical. So whatever it is, it's already justified in the literature. The initial guess is assumed to be all zero. So what is this class? What is the meaning of all zero? This is what you will face problem later on. You start asking question, why this is zero? Question is good, why it is zero? But this, if you want to know, then you have to go to literature review. That is, you have to go into calculus book or linear algebra books and you investigate on your own why this is zero. Because this is philosophical questions. So now we just give you an idea. Today, this part, we are not going to solve the problem, just to give you an idea. And next lecture, we will embark very rigorously on Gauss-Seidel method. So there is some information. You can see here the next slide. We are now in slide 23 about the convergence. Just now you calculated T0.1 at 0.2. This applies for all method, yeah? We have to test the convergence. This is what we call testing. Testing your output. How good is your output? So convergence is something to do with error. Of course, this word is not familiar to you because this is very advanced terminology. For further studies, masters and PhD, you have to investigate this convergence in the future. If you take up postgraduate studies or you take up any project or any research, you have to go into very rigorous. And this is where artificial intelligence is very important. Nowadays, we are talking about machine learning. We are talking about what we call deep learning, and then artificial neural network. There is a vast hundreds of methods in artificial intelligence to find the convergence. But we are not going to study all those things. Just to give you an idea, a simple one, how to calculate convergence for this topic. This is a general formula, yeah? It doesn't involve any method. General formula can be used for explicit, implicit, and then Crank-Nicholson method. Also, you can use for the Runge-Kutta, Young's method, and then Euler method. But you have to modify a little bit because this epsilon is called the convergence criteria. This is one of the very novel contribution to the this field. Because this convergence will lead to a very significant idea. We call it this is a very paramount to investigate or to explore the possibility of stability of the system. This is the world problem now, all over the world, across the globe. Stability of the system. This is very hard job. So one of the method in artificial intelligence is neural network. We call it ANN, artificial neural network. Now we already reached the level CNN, convolution neural network. All these methods are to study the stability and the stability related to convergence, and how good is the convergence related to methods and the outputs. So here we have a simple equation. What is convergence criteria? The symbol is epsilon. The delta, the length is modulus, because this epsilon is percentage. You calculate 40%, 30%, 20%. It's not a negative value. So that's why we put modulus. And then this is the equation, the right-hand side. But this epsilon s is the given value. So they want you to reach the convergence criteria, for example, less than 10%. In this case, the convergence, what we are talking about is the error. The error is less than 20%. This is the error analysis is very famous in statistics. But convergence is different. Convergence is very famous in numerical method. Of course, this statistic is very important because this error also related to convergence, stability, and so on. That you have to explore by yourself. So what we are trying to say is this epsilon subscript s is the given value. So you can minimize the error. Let's say they gave you 20% the error. But when you do the iteration, this is k plus 1. You see t superscript k plus 1 minus t superscript k divided by t k plus 1. What is k plus 1? What is k? Capital T is temperature. Just now you found the temperature at T 0.1 and T 0.2. So this epsilon for all I. the T1, T2, T3, T4 that you found for all I, where K plus 1 and K are the present and the previous iteration. So K is the previous, K plus 1 is the present. So you can do for the T 0.2 and 0.1 for each I. Let's say you get 20%, but they want the error less than 20%. So what you should do, you increase the iteration and you explore until you get less than 15%. That is the idea. Because you stop at T 0.1, 0.2, you continue 0.3, 0.4 and find the error until you reach this epsilon subscript s, then you stop. That is the meaning, class. So any question here, class? Any question here? Hello, any question so far? One, Amir?
No, sir. All clear, sir.
So we will not continue. I will stop in the next slide. And then we will continue next week. This example one, you see now, slide number 24. We are going to stop here, class. We will continue this because we want to apply the Gauss-Seidel method. So example one, it's look like same. Yeah, we are solving again. The reason is we want to do the enhancement, improvement. Compare with the explicit method. Is this simple implicit method good or not? That is the moral of this study. So use the simple implicit method to solve for the temperature distribution of a long thin rod with a length of 10 cm with the following values. Del x 2 cm, del t 0.1 second. At the time 0, the temperature of the rod is 0. And boundary conditions are fixed for all times. That means the temperature at x0 is 100 degrees Celsius. Temperature at x10 cm, 50 degrees Celsius. The value of K is 0.835. Find the temperature at T 0.1. So using simple implicit method. So in order to solve this equation, this problem, we will create a system. We will create the system with initial condition and boundary condition. So this part we will do next week. Okay, we will do next week. If you have time, you can do it yourself. But if you don't have time, it's okay. Definitely we will do in the next lecture because we have we just completed 24 slide. Another 20 more. Another 30 more slides. So another 30 more slides, we need just 2 lectures. So we can finish. Yeah, that's all for today, class. Any questions?
No, sir.
Any question, class? Any general question so far? Clear so far? Thank you, Muhammad Amir. Yeah. So that means, shall we stop here? So all the best, yeah? All the best. Happy weekend. Have a good day. Okay, so that's all class. Yeah, okay. Thanks a lot. God bless you.